It's time to do some math with Mr. Thomas the Math Train. Sometimes it's hard, but it grows your brain. Yeah. All right, I'll give you a few seconds to stop laughing and cringing about that stupid song. All right, so you should have just got your new math book, your Module 5 book. Let's open it up to the first page where it says Chance Experiments. And it doesn't really come right out and say it, but Module 5 is all about what mathematicians call probability. And probability is just what mathematicians say, where other people would say the chance of something happening. So lesson 1 is all about these chance experiments, which sounds like some big fancy thing, like, oh, setting up experiments with chance in it or whatever. It's nothing fancy. All it is, a chance experiment is anything that you do that you don't know the outcome of it before you start. So spinning this spinner right here, I don't know what color it's going to be. It was blue. That's the outcome, the fact that it came up as blue. And so just spinning this spinner was a chance experiment. If I had some dice and I wanted to roll them and see what numbers came up, that would be a chance experiment. If I had some different colored cubes in a bag and I wanted to pull those cubes out and see what color I would get, that would be a chance experiment. So just pretty much anything that could be like random. So let's talk about what we really mean when we say probability though. And I think the best way we could do that is if you turn over to this page here that has this thing that says a probability scale. In my book, it's page 4, but depending on whether or not you got the green book or the other version of the book, it might be a different page. Let me put a book under this page so it's easier to write. So we've got this thing called the probability scale, and this thing likes to pop up on SBA questions, so we should be like pretty familiar with it. What I want you to do is let's consider this thing that they've already given to us, the probability scale, like it says, obviously, right? But then we're going to make another scale right above it. And just draw essentially the same thing, a line about the same length. And here, where it says impossible and 0, we're going to write 0% up here. And then here, where it says 1 and certain, we're going to write 100%. And we're going to label this the chance scale and just write chance next to it. So probability literally just means the same thing that what people say when they say what people mean when they say chance, except mathematicians like to represent them a little bit differently when it comes to how they represent it numerically. So when we talk about chance in regular life, we usually say there's a 0% chance. If there's like no chance whatsoever something could happen, or in other words, we say it's impossible. And then when we know for sure something's going to happen, there's no doubt whatsoever, we say there's a 100% chance that's going to happen. And so we say that thing is for certain. And then if something's like right in the middle, maybe like a coin toss coming up heads or tails, and now hold on, I know there's people in every class period right now that want to go, wait, Mr. Thomas, when you flip a coin, it's not necessarily a 50% chance of landing with heads or tails because one side is heavier than the other, so it lands on that side more often. Or sometimes when you flip a coin, it lands on its edge and not really on a side. Or whatever. Okay, so when mathematicians talk about probability, they tend to ignore tiny little details like that, as far as like a coin being ever so slightly heavier on one side, or the 1 in a billion chance that it lands on the edge instead of a face or whatever. Let's not worry about that. You flip a coin, you have what people call a 50-50 chance, or sometimes they would say a 50% chance. Well, mathematicians don't like using these percents to represent chance because we can't really do math with percents. It's the same reason why when we started to learn about percents, recently, we learned how to convert them into decimals because we always wind up doing the math with the decimals. So mathematicians say, rather than representing something that's impossible as a 0% chance, let's just represent it as the number 0, and we'll call it probability of 0. And instead of representing something that's for sure as a 100% chance, let's just convert that to a decimal, and that's the number 1. And so if something is for sure going to happen, we just say it has a probability of 1. And then all probabilities must run between the number 0 and the number 1. You cannot have a probability less than 0. In other words, there's no such thing as negative probability. And you can't have a probability greater than the number 1, because once you go over something being 100% sure, that doesn't really mean anything. So every single probability must be a number between 0 and 1, and you can represent them as fractions or decimals, but almost always we're going to use decimals. It's so much more common to use decimals when it comes to probability, just because of the calculations that are usually involved, that I'm not even a big fan of this 1/2 being here right now. I'd rather it be 0.5. So this scale it sort of helps us like with what words we should use to go along with certain levels of probability. So if something has a probability of 0, it's impossible. If something has a probability of 1, it's certain or for sure. If something has a 0.5 probability, or other words, a 50% chance, then we say that thing is equally likely to occur or not occur. It has an equal chance either way. This is language that the book likes to use, and it's language that pops up on the SBA too. So for something to be unlikely, we say that it has about a 25% chance of happening, or as a mathematician would say, a probability of 0.25. I'm just taking the percent and converting it to a decimal. And then for something to be pretty likely, that would be something that most people would say has about a 75% chance. A mathematician would say a probability of 0.75. For something to be considered unlikely, like over here on the scale, it doesn't have to be exactly 0.25. I would say anything that's, really above impossible, right? As long as it's not 0, and maybe to like here, halfway between unlikely and equally likely to occur, is probably considered unlikely. You might even say that anything all the way up to here, just before 50-50, just before equally likely to occur or not occur, so anything in this like range right here could fall under the word unlikely. And anything in this next range, just past a 0.5 probability or just past 50%, all the way up to a 100% chance or a probability of 1, you could say falls in the likely range. So it doesn't have to be these exact numbers. All right, so what I want you to do is see these events here? It says events A through G. I want you to just label the probability scale with where each one of these events should essentially like where they should wind up on this probability scale. All right. There's like 7 of them. They should only take you, I don't know, maybe like 20 seconds each. How about we go, we'll go 2.5 minutes to do this. And I'm going to do it at the same time as you. So 30 seconds. And go. All right, so we're going to come back in 4, 3, 2, 1. All right, so hopefully your scale looks something like mine, and I already know what's going on. I've taught this enough times to know that, like, when you guys were reading scale event A and it says you will see a live dinosaur on the way home from school today, it's trying to come up with something absolutely absurd. We all know we're not going to see a live dinosaur on our way home from school today, but I know all you guys are already, but what if the guy from Jurassic Park got the mosquito out of the thing and he did the... All right, I get it. All right, B, a solid rock dropped in water will sink. When we put rocks in water, they pretty much always sink. But I know there's somebody out there going, oh, but what if it's the lava type rock that's kind of light? And as mathematicians, let's try to forget all the silliness that goes along with these sometimes, and just go with what we know is probably the case. And so the dinosaur and the temperature being negative 250 outside tomorrow, I put over here in impossible, probability of 0. The rock sinking, I put over here pretty much at certain, probability of 1. The disc with the 2 sides is essentially a coin, and the bag with 5 blue and 5 red, there's the same number of blue and the same number of red. So I'd say both of those were like a 50% chance, or a probability of 0.5. I think D here, well, let's see here, there's a spinner with 4 equal parts, labeled 1, 2, 3, and 4. So landing on a 4, you should have a 1 out of 4 chance. That's 0.25 probability, so I put that there. And E says your full name will be drawn when a full name is selected randomly from a bag. So how many students are in this class? Anywhere from 25 to 30, depending on what period it is. So you got like a 1 out of 30 chance of getting selected. So I put that way over here, like not all the way to impossible, but pretty close to it. So next, down here below, you might not be able to see because my thing's not pointed at it right. Let me move this real quick. It says, design a spinner so that the probability of spinning a green is 1. So probability of 1 means it's for sure going to happen. There's no way it can't not happen. Yeah, I think that's what I meant to say. And so design a spinner, it means like draw a circle and then label it so it comes out exactly what it's saying. Well, if the probability of spinning green has to be 1, then the whole thing has to be green. There has to be no other possible outcome other than green. Yes, I used a blue marker to make a green thing when I had a green one right here. I don't know why I did that. So now over here on the next one, it says design a spinner so that the probability of spinning a green is 0. So this one can't have any green on it. And just to stick with my habit of not using colors correctly, I'm going to use green on a spinner that can't have any green on it. It can have whatever other colors we want, and it could have stuff that's not even colors. It could, let's say we split it up into like, I don't know, this many pieces. And they don't even have to be equal sized. We can make them like weird sized. And this one over here says cat, and maybe this one over here says 2, and this one over here says red, and this one over here says, I don't know, tuna, and you figure out what the other one's going to say. Essentially, as long as it doesn't say green, then there's no probability, or I should say a probability of 0 of getting green, and that's what the thing wants. All right, so I'll let you do number 8. Design a spinner with 2 outcomes in which it's equally likely to land on red or green. And then I want you to continue on, read this stuff here, and write your own answers to these 2. And then I'll write my answers while you do yours too, and then I'll show you my answers, and then that's probably going to be all we'll do from this. So I don't know, how about three minutes to do this stuff? Let's do that. Go. All right, we're coming back in 5, 4, 3, 2, 1. All right, so this is what I made during that time. So they wanted a spinner with 2 outcomes. So red and green are my 2 outcomes, which it's equally likely to land on the red and the green parts. So I just had to make sure it was like a nice even split. I drew it as best I could. As long as your red and your green parts are like even sized, then they should be equally likely. So the next part says, an event that is impossible has a probability of 0 and will never occur no matter how many observations you make. What do they mean by observations here? This is just like your number of tries. Like if you're spinning a spinner, right, where did I put the thing? Here it is. So if I'm trying to see the probability of getting a yellow and I want to test it, I could flick. Okay, I got an orange that time, but I observed it come up orange, so that would be 1 observation. Spin again. All right, purple, so that's 2 observations because I observed it come up purple. And however many times I try this, that's observations. So let me reread this now. It says, an event that is impossible has a probability of 0 and will never occur no matter how many observations you make. This means that in a long sequence of observations, so like if you did it a lot of times, it will occur 0% of the time. An event that is certain has a probability of 1 and will always occur. This means that in a long sequence of observations, meaning you did it a lot of times, it will occur 100% of the time, or every time. And so then they asked you, what do you think it means for an event to have a probability of 1/2? So I think what it means is that if you try whatever the thing is, you have a lot of observations, a lot of times, then the thing should happen. The vocabulary we're going to start using pretty soon is we will say the desired outcome should occur. But right now, since we're still kind of learning this stuff, I'm just going to say the thing should happen about half the time. Or actually, if you did it an infinite number of times, you should get exactly half. So what's the importance of the long sequence of observations, or saying that we have to do it a lot of times? I want you to think about a coin flip, and yes, we're going to just pretend that coin flips are magically 50-50, 0.5 probability, none of the other stuff. You could flip it like 1 or 2, like 2 times in a row and both get heads, right? And so you didn't get 1 head and 1 tail like you would think you're supposed to get because it's 50-50 or whatever. You could flip a coin 4 or 5 times in a row and get heads every single time. So we don't necessarily, it doesn't have to go back and forth like half and half. And it doesn't necessarily always have to be exactly half. Maybe you flip the coin 20 times and you get 14 heads and only 6 tails. We know that it doesn't have to be exactly half the time. But there's this sort of like mathematical phenomenon, or there's just this thing we understand scientifically, that if we flipped the coin 1 billion times or 1 trillion times, we actually would expect it to be pretty much exactly half. We would expect if we flip that coin 1 billion times, then it better be about 500 million heads and 500 million tails. And that's just because sometimes when we try things a few times, we get unexpected outcomes, like a few times in a row, but it's super duper rare for that to happen over a long period of time, to get a bunch of unexpected outcomes. Over time, we expect things to happen pretty much the way we expect them to happen. So that's sort of the importance of the word a lot, or the long sequence. It just takes out the sort of weird things that can happen when we only try something a few times. And so next it says, what do you think it means for an event to have a probability of 1/4? Essentially the same answer as what do you think it means for an event to have a probability of 1/2, but instead it's, if you try it a lot of times, it should happen, oh dang, I wrote the wrong thing. I wrote half the time. That's not right. It should happen 1/4 of the time. And just like the coin flip, we know that that doesn't necessarily mean it's going to happen exactly 1/4 of the time. Like if we try it 4 times, it better happen exactly 1. It could happen all 4 times. Or it could happen none of the times. But if we tried it 1 billion times, we would expect to see pretty much exactly 1/4 after that many times. All right, so let's see here. Let me see if there's one last thing I wanted to say before you move on to your next thing? I think actually not. I think we're good. So your substitute or Mr. Turner or whoever's with you right now is going to hand you a worksheet like of notes to take while you watch this Bill Nye the Science Guy episode about probability. So yeah, I think that's it. I'll see you guys tomorrow.